So before we start with the lecture proper, I'd ask you for you to recall the last lesson we had, basically on the LC circuit discussion and how it hinged to being a spring mass system analog because the differential equations look the same. So maybe if we went back to how we discussed the spring mass system, we can have an idea on how the LC circuit will look like. And true enough, this comparison is reasonable because the differential equations themselves, so it's for the mechanical system, it's the equation of motion. For the LC circuit, it's the equation for how the charges change with time. The differential equations that govern them share almost the exact identical forms. So you can see here that, okay, instead of x being the variable for the mechanical system, we have q for the circuit. And then this k over m term, which is omega squared for the mechanical system, will be replaced by 1 over LC squared for the circuit. Because of this, the solutions themselves share similar forms. So it's a cosine omega t for x, it's q cosine omega t for q. And of course, we usually do away with the phi depending on how your initial systems look like. And then if you take the first derivative for x, you get v, or the movement of the mass. For the right side, for the LC circuit, you have I of t, which is the movement of the charges with respect to time, or the change of charge with respect to time. It's not only in the equations of motion that LC circuits look identical or very similar to the spring mass system, but also in their energy conservation equations. For the spring mass system, it would be the kinetic energy and the potential energy that come into play. And the potential energy comes in the elastic potential energy form, so it's 1/2 kx squared. For the LC circuit, it's the magnetic energy given by 1/2 Li squared and the electric energy given by 1/2 CV squared or 1/2 Q squared over C. What is important though is that the LC circuit is idealized in the sense that energy loss has not been considered yet. Clearly, energy loss is something that we are mildly inconvenienced with, as you can see in your electric bills. So for most real circuits, resistance R is almost never zero. The only exception is when you have superconducting circuits. To continue the analogy, let's say that the loss of energy in mechanical systems was introduced by frictional forces, and it is the case because when we introduced non-conservative forces into the mechanical system, what happened is there was an energy loss, or not energy loss, but your energy is converted to thermal energy in terms of heat. Since power dissipated in the circuits meant that energy was lost to heat, the loss of energy can then be attributed to resistance. Because way back then in a couple of lectures ago, when we discussed circuits, the power through a resistor is basically power dissipated as heat. So it begs the question, how do we factor resistance in our LC circuits? The answer may be pretty simple, but then the fact that we add resistance or that we consider resistance in LC circuits means that our differential equation is going to change. The answer is pretty obvious. You factor in resistance in circuits by slapping a resistor in the circuit. So this is our LC circuit. All we need to do is draw something like that, and then you have cute little R there. The question then would be, what would its analog in the spring mass system be? Because we haven't really considered the dissipative forces in the mechanical system. We did already, but not in this discussion yet. This leads us to lecture 31 of Physics 72, which focuses on the LRC series circuit. This is found in chapter 30.6 of University Physics. So we only have one objective for this lecture, but then we may focus primarily on charge and we can leave voltage and current to a later lecture. Now we introduce the LRC series circuit as the LC circuit with just a resistor that's added here, as was drawn a while ago. The order of placement shouldn't really be important because when you do Kirchhoff's law, you could rearrange the terms later, so we'll be there in a bit. A resistor may not be even included, considering that instead of having a resistor, we consider the internal resistance that the inductor has, or the resistance that the wires possess. And one more thing, for the purposes of this lecture, we won't include the power source in the differential equation. So now it's just a capacitor, a resistor, and an inductor. So with the addition of resistance, what it does is the electromagnetic energy in the circuit, electromagnetic being electric energy of the capacitor and the magnetic energy of the inductor, this electromagnetic energy will be converted to other forms, namely thermal energy in terms of heat. So the introduction of resistance converts this EM energy into something that's irrecoverable. The dissipation that resistance brings to the system is akin to friction in most mechanical systems, particularly the spring mass system. The spring mass system can have friction present on the surface, so previously we didn't really consider some frictional force. This time we consider that a rough surface is present and the mass that moves along it is affected by this rough surface. So what it does is it effectively slows the block and it shortens the extension of the spring with each successful cycle until at which point that the system stops. We can expect the same for the charges in the LRC circuit because eventually after some oscillations, the charges will stop increasing in the capacitor, or even for very high values of resistance, it won't even oscillate or it won't even complete a single cycle. But we'll get to that in a bit. Okay. Since resistance will eventually cause the charges to stop moving because it will drain all of the electromagnetic energy, the capacitor must first be charged by some EMF source, as you can see here in the top. This battery, if you will. And what happens is, this switch basically closes the top loop. You can call this the charging loop. And that if the switch is in this position, the EMF will charge the capacitor. So we're not really considering any changes due to the inductor and the resistor for now. So in step 2, if you flip the switch to the other side, it disconnects the capacitor from the source, but it then connects it to the inductor and resistor in a series connection. And then you close the loop at the bottom. The charges move on the lower loop and it will oscillate until the resistor converts all of the EM energy to heat. From there, you can flip the switch to recharge C again. Again, we need this charging because eventually all of the energy that the capacitor has and that the inductor has will be converted to heat because of the resistor. So to continue the movement of the charges in the LRC circuit, you're going to have to flip the switch every now and then. So to start the discussion of getting the differential equation for this circuit, we say that the capacitor is fully charged at the start upon switching it. And then we also say that the current is equal to 0 because we just flipped the switch. Now, using Kirchhoff's loop rule, take note of the current, it's moving clockwise. And for ease of calculations, we also dictate that the path that we're going to traverse is also clockwise. We're going to get this equation. Here VR equals minus EL minus VC equals 0. And then from our past lessons, Ohm's law for resistor, the inductance lesson we had, and the capacitor potential drop from a few lectures ago, we end up with this equation. And then we need to get an equation in Q. So we need to change this variable I. We know that current I is just the rate of change of Q with respect to time. And then we isolate the second term, which will be a second order derivative. We eventually get this equation, this differential equation for the LRC circuit. And I'd like to note two things. Firstly, the EMF source is not included. We just added R into the system. And let's do things one at a time. And notice that with the exception of this term, let's say you remove that term, you'll end up getting the original equation that we've had in the LC circuits. I'd like to point out something that's rather important because for this LRC series circuit, getting the solution will be a bit different. For the LC circuit, or for the spring mass system, we only looked for one particular solution and it worked to our benefit because we didn't really have to consider so much the values of K or M, or for the LC circuit, L and C. Because of this second term in the LRC series circuit, there are different solutions that depend on the values of the circuit elements, C, R, and L. This isn't much of a big deal because in Physics 71, when we discussed damped oscillations, or the spring mass system, we didn't really look at the solutions themselves. We looked at the graphs, and we looked at a particular value to see whether the system was overdamped, underdamped, or critically damped. So let's start with a few cases. Let's work with the simplest one. If R is equal to 0, what happens is, okay, the second term can go bye-bye, and it reduces to d squared q over dt squared plus q over LC equals 0. And this is something familiar because this is just the LC circuit equation from last lecture. So similar to Physics 71 and how we discussed the LC circuit, we're not really going to solve the differential equations for the LRC circuit. Our focus will be on the qualitative properties of the solutions and their graphs. So if you remember, the spring mass system, the damped spring mass system, has three types of behaviors. And we can discuss the LRC series circuit similarly. It also has three behaviors: underdamped, critically damped, and overdamped. Now let's start with the underdamped solution because it's the one closest to the LC circuit behavior. Now, this underdamped solution leads to the charges oscillating back and forth in the system, and it decreases in energy in each cycle. The solution function itself is long, but we can split it to three parts, or three factors if you will. The first one in purple is the maximum charge at the start. We can call it A, we can call it Q. And then the second term, the one that's pretty new to this problem, we call it the damping factor or the decay factor, because this tells you that, okay, as time passes by, the amplitude of your oscillation will be smaller and smaller. We'll get to that later when we see the graph itself. And finally, we have a rather new term for the angular frequency, the one that's multiplied to time. So if you notice, for the LC circuit, our angular frequency was actually just this term, 1 over LC. That's because we considered R equals 0. There was no resistance in the discussion of the LC circuit. And now that our R value is not equal to 0, we have to consider this little term here. Okay, we said in previous slides that the nature of the function churned out by the differential equation depends on the values of R, L, and Z. Now let's be more specific. This behavior can actually be seen in the omega prime term, which contains all of the three terms. So you have L here, as well as here, you have Z here, and you have R here. All of those three terms basically tell you how your solution is going to look like. And it's omega prime that best summarizes how the nature of the functions will be. So firstly, for the underdamped oscillation, you want your resistance value to be weak enough so that it doesn't really vary or it doesn't really change much or deviate much from your LC circuit solution. And it kind of makes sense. And then this function here, or this inequality here, sorry, is based on whether omega prime will actually be greater than 0. So the nature of omega prime will depend or will dictate to you what type of solution you'll have. And the second term is, okay, what if our resistance is actually at a specific value that it makes omega prime 0? So in effect, remember that this omega prime term arrives in the cosine omega prime t part of our underdamped solution. And it will only make sense, our oscillation will only be present if this omega prime is not equal to 0. And the moment this is equal to 0, you'll end up with a cosine term that's not really dependent on time. So if it's not dependent on time, it won't oscillate. And then that brings you to your next two equations, which will have different solutions. The critically damped solution will have omega prime being equal to exactly 0. And then the last part is if your R squared, or if your R is high enough, it eventually slows the charges down. It will not oscillate, but it will also decay very slowly, and you'll have your overdamped solution. This leads to an omega prime that is actually imaginary. Look at the omega prime. Omega prime is a square root, and square roots can never be negative. So we're not really considering what happens if omega prime is negative. But then what's inside here? If R squared is actually greater than 4L over C, you'll have a negative argument in your square root function. And what happens is you'll have an imaginary term. And we haven't really discussed what happens if you have an imaginary angular frequency. This is one of the reasons why we're not really delving too much into the shape of the solutions themselves, but rather the graphs of the solutions. So we're going to focus on the behavior of these graphs. We focus on how the graph looks like for each of the cases, but let's start with the underdamped case as it's the one that's closest to the LC circuit's behavior. It's not the graph yet. This isn't the graph yet. We'll get to there in a bit. With R squared less than 4L over C, or basically a weak resistance value, its resistance will be small enough to allow the movement of charges back and forth. So the only difference is, even if your r squared is small enough, it's not equal to 0. Because of this, your function and the added flavor from the LC circuit case is that this oscillation is now sandwiched or modulated by a damping exponential or a decay exponential, as seen in the one in blue. Okay, so by multiplying this term to the old solution being qt equals a cosine whatever, we effectively get an oscillation that shrinks with time. So if you recall, this term, this envelope, will probably look something like this. Okay, and I can expect that if you multiply this thing with your oscillation, you'll end up having an oscillation that shrinks with time. Now, the oscillation frequency won't change, it's just the amplitude that will. And true enough, when you have the solution in green, and then you impose it with, or if I graph the modulating envelope as well, and keeping in mind that I'm also going to place 1 at the bottom, you'll end up with an oscillation that is modulated by this envelope. So it's basically trying to shape your oscillating frequency into something that's modulated by this function. It's kind of like how funny looking ice cubes are made using casts. So I'd like to remind you that the resistance affects not only this damping term, but also the angular frequency. Moving on to the second case, we consider a condition where r takes on a specific value. This r squared equals 4l over c. This makes the omega prime term equal to 0. And then it leads to a solution where the cosine term is rendered useless. So we can't really apply the function that we used for the underdamped case. No oscillation will be present in the system. This behavior of the capacitor charge would then be a quick but smooth decay to very low values. So at the start, you have your initial charge here, and eventually it tapers down until it reaches 0, keeping in mind that the charges will never actually be negative. So talking in advance, this decay will be will actually be faster compared to the overdamped case, and we'll see this in the next slide. Now I should remind you that the solution for this case is not at all like the underdamped term, and it looks somewhat intimidating. But then again, to the benefit of most, the solution will be out of scope for Physics 72. Now, the overdamped case basically turns our R value high enough so that the omega prime will actually be imaginary. This means that R squared is greater than 4L over C. What happens is the overpowering resistor disallows charge oscillation, similarly to the critically damped case, but this time it's strong enough that its delay for the decay is longer than in the critically damped case. Now, the solution is a long one. I'm not really going to show you because it might intimidate you, so I'll keep it hidden for your peace of mind. Now, in summary, superimposing all of the graphs gives us an idea that while the solutions of these cases look wildly in their functions, their behavior and how they're graphed is not too far from each other. As a summary, positive omega prime admits the underdamped case, 0 omega prime admits the critically damped case, and an imaginary omega prime leads to the overdamped case. Now we consider that only underdamped cases oscillate, and the larger that the resistance R is, the longer the decay occurs, and you can actually see it here. Notice that the green graph is the one that decays the fastest, because the resistance value is weakest. Then you'll have, for the critically damped case, you see the one here in orange. Sorry, bad color. The one in orange it's going to decay a lot slower compared to the underdamped case because you have a resistance value that's higher. But then if you compare it to the overdamped case is also going to decay but at a much slower rate. And you can easily see this in the graph, but not so much in the solutions. So it's actually advisable for you to, when understanding LRC circuits for the first time, to check the graph more than the solutions themselves. Now, you could also see here that the effect of R in your graph is when you have a low value of R, the changes in your currents or the changes in your charges in the capacitor as well in the system will be much more pronounced. But then if the value of your resistance is high, it will take a longer time for these values of charges to actually change. And finally, as a supplement, let's look at our qualifying condition. We relate R to the ratio of L and C. So we're going to check the relationship of R here and L over C here because they're the ones that dictate our behavior. High values of L tell you that the circuit will try to counter changes in the current as much as possible. A higher value of inductance means a higher resistance to changes in currents. Remember that dissipation of energy changes the current, so L actually tries to fight this dissipation. High values of C mean that it will take a lot of charge to change the voltage value. This means that a large C means a slight change of voltage introduced by the resistor in terms of dissipation demands a lot of charge actually. So that means a slight change of voltage will require a lot of charge if you have a high value for capacitance. And this can wear the system fast. This may give some intuition to why we relate R to the ratio L over C in dictating whether the flow of charges is powerful enough for oscillation or will it succumb to a slow decay to zero. So let's try to answer some quick exercises to help us master the concept better. You consider an LRC circuit. What will happen to the frequency of oscillation of the capacitor's charge if the resistance is slowly increased? So we're just going to ramp up the value of resistance. Now we assume that this oscillation is underdamped throughout the process, and then you have four choices. The frequency won't change, the frequency becomes larger, or the frequency becomes smaller, or you go straight to the charge will no longer oscillate. Obviously choice D is incorrect because we're going to make it stay underdamped. Now, as a hint, when you answer this problem, remember how omega prime looks like, because it's omega prime that actually tells you whether you're going to oscillate or not, or how your oscillation looks like. So, omega prime is going to be 1 over LC minus R squared, I'm speaking as slow as I write, and 4L squared. And then your R squared is actually this term here. And that should tell you what the trend should look like. So as your omega is your subtrahend, a higher value for R will just give you a smaller value for omega prime, sorry. And that should mean that your frequency will become smaller. The answer is C. Let's answer another problem with a focus on specific values for R, L, and C. An LRC series circuit includes a 2 ohm resistor. At t equals 0, or at the start, the capacitor charge is 2 microcoulomb. Now, for which of the following values of inductance and capacitance will the charge on the capacitor not oscillate? We know that the system will not oscillate for critically damped. So when you have critically damped, you'll have this condition, and an overdamped case. So you have this condition. All you need to do then is to check which of these choices arrive at these relationships for R, L, and C. An easy way to go about this is, okay, you're just going to subtract R squared with 4L over C, and to see whether the solutions will be equal to, or this expression will be equal to 0, or will it be greater than 0? Because that should tell you if it's equal to 0, it's going to be critically damped. If it's greater than 0, it's going to be overdamped. So for choice A, we will receive an overdamped condition, so it should be one of the answers. So choice B has a large enough inductor or inductance to offset R, so it actually leads to underdamped oscillations, so no go. Choice C will lead to a critically damped result, so it's also one of the answers. So for this lecture, all you need to do is to look at the relationship between R, L, and C to determine whether your system will be overdamped, underdamped, or critically damped. That's it for the intro to LRC circuits, and thank you very much for listening.